Hi, I'm Scott Burleigh, a longtime member of IPNSIG, and I'm going to be telling you a little bit about the architecture for solar system internet, which we've been working toward for quite a long time. First, by way of background, I'll say a little about what we mean when we say solar system internet. After that, I'll talk briefly about the document that lays this idea out in detail, the Solar System Internet Architecture Green Book, published by the Consultative Committee for Space Data Systems. I'll talk about the motivation for building a solar system internet from the perspective of the world's national space agencies. I'll say something about what infrastructure the agencies are going to have in place to make it work. And I'll briefly mention some of the mission data management that will be involved in our network. Then I'll describe how we believe we can get from here to there with some illustrations of the kinds of data flows involved. I'll go into a bit of detail on the three stages of that transition. Then to wrap up, I'll talk briefly about how IPNSIG is involved in building out this architecture and the institutions that will have to be in place to make it a success. First, what is a solar system internet? Clearly, it's possible to have communication between Earth and spacecraft over interplanetary distances. We have been doing it for a long time using current technology and procedures, and this is not what we mean by solar system internet. The solar system internet will enable any entity connected to the network to send data to any other entity connected to the network at any time without requiring human intervention at any point, just the way the internet works. The data may arrive a long time after they were sent, which will not be internet-like because of signal propagation latency and lapses in connectivity. But normal operation of the network is lights out. This is not people driving all of the communication links at all times. So let me just emphasize this last point. The solar system internet will enable end-to-end transmission without the need to manually revise retransmission timeout intervals on gateways or shut nodes down on loss of connection, restart them when mutual visibility resumes, or revise static routing tables whenever orbital movement results in changes to network topology. It will function automatically end-to-end like the internet, except over round-trip times measured in hours or days. The solar system internet is described in detail in this document published by CCSDS in 2014. And this is a public document. You can download it from this link and read it yourself. It is the consensus view of most of the world's national space agencies. The concept that an interplanetary internet, as envisioned by CCSDS, would look like this and work in this way with these elements of software, procedure, and organization. From that document is this statement of the rationale for developing the document. The rationale essentially is that the interagency operations advisory group, which is founded by the Space Agency's interoperability plenum several years ago, to be a forum for identifying common needs across multiple agencies relating to mission operations, space communications, and navigation interoperability, that the IOAG has identified the desirability of having a solar system internet in a document called SSI Operations Concept. And this document was the definition of that architecture in detail. Here's the business case underlying that rationale. The consensus of the space agencies is that solar system internet will make spaceflight missions essentially less expensive and more successful. They'll do that by enabling failover in the event of failure, additional routes so that temporary occultation of a spacecraft in one direction won't prevent it from being able to communicate by a different relay point pointing in a different direction. by agreeing to cross-support missions of each other's agencies, it is thought that each partner agency can gain the benefit of shared resources and infrastructure. Of course, like any network, the SSI will need hardware to run on, as described here. In particular, additional computing equipment at Earth stations. And the operation of the network will need to be managed in the context of the space agency's own resource limits. So there may be agreements for resource sharing, maybe resource compensation and reimbursement. All of that is going to need to be worked out in detail to make the solar system internet work in the long term, much as is done in the internet agreements between internet service providers. How do we get there? Here's a simple illustration of the way spaceflight mission communications are typically configured today. There's a spacecraft, there's an Earth station. The communication directly between those two is by radio frequency transmission. The horizontal black lines here are showing the information flow that is enabled by that radiation of radio signals between the spacecraft and the Earth station, and that the information carried over those signals is mission and engineering information that would go to the Mission Operations Center for instruments on board the spacecraft, engineering information for the spacecraft itself, and engineering information for operating the Earth station. And here is a representative slice of what we're aiming for in the long term. Here we're seeing not the communication structure for a single mission, but the communication structure for 3 missions, 2 of which are operated by one agency and 1 of which is operated by an entirely different agency. And that functionality enables, for example, transmission between a spacecraft mission operations center at agency Y to take over in the event of spacecraft mock failure for mission B, by enabling relay through agency Y's mission C spacecraft up to the lander operated in mission A, and from there back down to the operations of that spacecraft. What is proposed here is that migrating spaceflight mission operations from the current model to this network architecture should be undertaken in 3 discrete manageable stages. Mission functionality, internetwork functionality, and advanced functionality. And it's important to observe here that organizations participating in the solar system internet could operate at any of these 3 stages, but in order to gain maximum benefit from participation in the network, they will eventually need to migrate toward the more complete functionalities that are contemplated in the transition plan. So here's stage 1, which is basically just the automation of existing mission structures. It would look a bit like this, and what we're seeing here is migration from the intentionally managed communication links in current mission operations architectures to an automated small network. I think of it as a subnet so that the cost of operating the mission is reduced just by means of the automation, the introduction of the delay-tolerant networking technology. The organizing principles at this stage look like this. The coordination provision of the data communications is entirely internal to the mission, same as it is now. There may be interagency cross-support, but the agreements are ad hoc, and they're negotiated privately. There's no formal structure for making it happen. There may be cross-support of link layer services, and that also is privately negotiated. In order to reach stage one, the agency operating a mission that is going to participate in the solar system internet needs to establish these kinds of procedures. Procedure for installing solar system internet nodes, which is to say DTN nodes, requesting solar system internet service is a bureaucratic function. Publishing contact plans, that is, publishing the opportunities for transmission that are going to be made available for mission communications. Issuing data from one node to another node. The bundle protocol application programming interfaces are used to do this. Reporting on the operational state of a node, the same sort of thing. Troubleshooting the behavior of the network, modifying the configuration of the node after it's been established, sending emergency commands, estimating the time that a bundle will be delivered. Basically, what's happening there is delay-tolerant networking technology being adopted in the context of isolated individual missions. And on stage two now, we see the advantages of mission interoperation beginning to accrue. The management of that operation is not yet automated, so the scalability of the network at this stage is limited. But the missions are able to participate, and those that are able to participate begin to reap some of the benefits of the architecture. Here's what stage two would look like, a simple subset of the overall network. You've got multiple space agencies, multiple mission operations authorities, multiple missions, and they're able to cross support. For example, if the science spacecraft for Authority A's mission is temporarily unable to communicate with its mission operations center, what it can do is communicate with a relay spacecraft operated by Authority B, which in turn can move the data through its own Earth station, and from there, by means of the terrestrial internet, over to the science spacecraft mission operations center, so that the Authority A spacecraft information is still available to the science spacecraft mission operations center, even if the spacecraft is, for example, on the other side of the moon. And here's where we see the beginnings of the network administration structure that will need to be developed to make that all work. We need a coordination function that you didn't need before, because we've got two mission authorities that need to cooperate. And there could be any number of additional authorities in addition to these two, and they would all need to participate in this coordination function to enable the reception of data by spacecraft B from a lander operated by an entirely different mission authority. The organizational principles at this stage are more extensive. They go well beyond the mission operations structures for the flight missions we've seen over the past 10 years. A provider node can support a mission that is under different authority. Provider nodes that are supporting a given mission may be under multiple authorities, and that is um, shared operational responsibility in making a single mission work. But at this stage of solar system internet implementation, the coordination of mission data communications is still not automated. It's negotiated among the authorities, the space agencies. There has to be a coordinating function that makes that negotiation happen. It's a managerial function rather than an automated function. And at this stage, the number of additional functional procedures is relatively small because most of the work of getting things operating in automated fashion was adoption of the delay-tolerant networking technology, and that happened in stage one. What's needed in addition is mechanisms for requesting cross support and for publishing the composite contact plan, that is, not just the individual contact plans for individual missions, but the union of those so that cooperating agencies can see opportunities for transmission in other agencies' contact planning and negotiate access to those transmission opportunities. Finally, in stage three, the manually supported network administration functions themselves begin to be automated, enabling the solar system internet to scale up to the vision articulated in the Solar System Internet Green Book 10 years ago. There is automated coordination of mission data communications so that the pairwise conversations that enable interoperation in stage two are expanded to be able to involve large numbers of cooperating authorities in an automated fashion and enable that cross support to scale for very large numbers of missions. At this stage, only a single new operational principle is established, that is the automation of mission data communications coordination. And a few new functional procedures are needed at this stage. In order for all of this coordination to happen automatically, there has to be sufficient trust to enable commitment on the negotiated agreements. That entails distribution of security keys, the ability to revoke security keys, and also network-wide troubleshooting rather than troubleshooting just within the context of an individual mission, and network-wide problem remediation. IPNSIG, the interplanetary chapter of the Internet Society, is enthusiastically involved in efforts to define the scope of this architecture, and especially to assist in designing network governance procedures that will assure the smooth operation of the network as it's extended to support space industry and exploration over the coming decades. And here are a couple of closing thoughts. It is certainly true that the number of humans living off Earth in other parts of the solar system is likely to be pretty small for a while. It's very expensive and dangerous to put people in space. But the number of robots operating away from Earth and the number of humans on Earth concurrently monitoring and controlling the robots may increase dramatically over the next few decades as space industry begins to be built out. All of these entities will need to communicate among themselves. The simplicity and resilience of the solar system internet will enable the complexity of these communication relationships as they're continuously sustained to scale up without limit, very much like the way the internet works. It has taken a long time to reach the point at which we're beginning to see stage one of the transition to solar system internet. Space is a harsh environment. It's difficult and expensive to inhabit, but we are getting there. Thanks.